We are working Practice Test B, Objective 4. We are being asked to calculate enthalpy changes that occur using a warming or cooling curve and including phase changes such as melting, freezing, boiling, or condensing. I've read my first questions. It's asking, how much heat, measured in kilojoules, is released? I made note that those are important words to let us know that this is an exothermic process. We'll note to make sure that our delta H is negative at the end. We're calculating for kilojoules of heat released when 150 grams of steam, keeping track of the mass of water, 150 grams, that we'll be working our problem for. We're beginning at 155 degrees Celsius and we are converting to ice at negative 20 degrees Celsius. The rest of our question is letting us know those standard values for heat change as well as specific heat values. We've recorded those particular pieces of information on our test-taking tool page. When I'm taking Objective 4, I would definitely have out my test-taking tool. I'll scan out so we see what I'm looking at. We've written a phase diagram for water, and each one of those 5 line segments are giving me important information at the bottom. We have this. We should have it out for Objective 4. So again, the further information in this particular objective is just helping me find each point on the line segment, the values we'll need to calculate. Let's begin by drawing our XY axes, and I've labeled the Y-axis to be temperature in degrees Celsius, and joules of heat energy go on the X-axis. The first temperature given to us in our problem is 155 degrees Celsius. I'll write that at the top end of my temperature scale, 155. We are then converting down to solid ice at negative 20. We'll record that as our next important temperature, negative 20 degrees Celsius. We also need to consider any temperature between 155 and negative 20 in which water would undergo a phase change. We know that water will change phase from the gaseous form to the liquid form at 100 degrees Celsius, and we also know that water will change phase once more from liquid to solid at 0 degrees Celsius. On this particular graph, we have 4 important temperatures as we develop our line segments. When we look at the first segment, I'll call point A to point B. The first line segment is simply a cooling curve from point A to point B in which the steam is releasing heat energy as it drops its temperature. At 100 degrees, we notice there will be a flat line on this graph where a phase change occurs. From point B to point C, we label that the heat of vaporization, turning from the gas to the liquid form. Once all of the molecules at point B, which were 100% gas, have converted to the liquid form at point C, you'll notice a drop in temperature. In the liquid form of water, between 100 degrees and 0 degrees, as we're removing energy, we will take a look at a drop in temperature. At 0 degrees, where we reach point D, it flatlines again. From point D to point E, we would call that a phase change called the heat of vaporization. And finally, from point D down to point F, we are in the ice form. Up high is steam, in the middle range is liquid, and down low is ice. We have 5 different line segments on this curve to consider. What we will do is solve 5 separate problems, sum them to find our final answer, the heat released when 155 has cooled down to negative 20. In our first line segment AB, we said that it was steam. Line segment B to C, we called that a heat of vaporization, the process of changing phase. Line segment CD, we labeled that as liquid water. Line segment D to E, we labeled that as a heat change known as the enthalpy of fusion, going from the liquid to a solid, a phase change. And in the final temperature change there, point E to point F, we know that that will be where we will calculate for ice. Knowing that whenever we change temperatures, as in the line segments that have a slope, Those are MC delta T problems where we need the mass of the water. However, where we have flat lines during phase changes, we need to know the moles of water. I like to have both of those quantities ready before we begin even calculating.